Hello, good morning, students, dear students. Today, continuing with the module 3 of association analysis, the last video on module 3. So, we're going to see rule generation. So, what is rule generation? We'll see in detail. So, rule generation, this section completely describes you how to extract the association rules efficiently from a frequent item set. When you have a set of frequent item sets, from that we need to extract some association rules. How that can be done, we'll see in this video. So, let us assume we have a frequent item sets and that item set is having k items. So, now if you take y can produce up to 2 raised to k minus 2 association rules. So, if you take k item sets, then how many association rules can be generated? So, it can be around 2 raised to k minus 2 association rules can be generated, ignoring the item sets that are empty. And association rules can be extracted by partitioning the item set into two non-empty item sets. So, what are those two non-empty item sets? One is x and one is y minus x, such that x belongs to y minus x. So, here again both x and y minus x should satisfy the confidence threshold. And whenever I form a rule x belongs to y minus x satisfies the confidence threshold, make sure that it also satisfies or it has already met the support threshold, because they are frequent item sets. As the item sets are frequent item sets, they have to satisfy the support count also. So, let us take an example. Let x is equal to 1, 2, 3 be a frequent item sets. I have 3 frequent item sets. I have an item set x which is having 3 items 1, 2 and 3 be frequent item sets. So, how many association rules can be found from this? So, there are around 6 candidate association rules that can be generated from this x. So, with 3 items 1, 2, 3 which belong to an item set k x. So, how many association rules can be generated? 1 2 belongs to 3, 1 3 belongs to 2, 2 3 belongs to 1, 1 belongs to 2 3 and 2 3 belongs to 1 3 and 3 belongs to 1 2, as each of their support is identical to the support of x. The rules that satisfy the threshold means x of 2, x of 1 comma 2 is also having the same threshold as that of 3, means x 1 of 2 1 comma 2 also satisfies the support count and the 3 also satisfies the support count. So, like this all the 6 candidates satisfy the support count. Now, coming to the confidence, computing the confidence of an association rule does not require additional scans for the transaction data set. So, now support count, for calculating support count we need to scan the database, but to calculate the confidence we need not to extract or we need not to scan again the transaction data sets. Consider one rule, the first rule 1 comma 2 belongs to 3, which is generated from the frequent item set x 1 comma 2 comma 3. The confidence, what is the confidence for this rule? 1 2 3 divided by 1 2, because 1 2 3 is a frequent item set. The anti-monotone property support ensures that 1 2 also must be a frequent item sets. Since the support for both the count both the item sets were already found during the frequent item set generation, there is no need to read the entire data set again. So, now confidence rule pruning, confidence based pruning. Unlike the support measure, confidence does not have monotone property. So, as you know, support is having anti-monotone property, but the confidence does not have anti-monotone property. For example, x belongs to y can be larger, smaller or equal to the confidence for another rule x dash of x dash belongs to y dash, where x dash is a subset of x and y dash is a subset of y. Okay, so now here nevertheless, if we compare the rule generated from the same frequent item set, the following theorem holds for the confidence measure. Now, what is the theorem for the confidence measure? So, if a rule x belongs to y minus x does not satisfy the confidence threshold, then x dash belongs to y minus x dash, where x is a subset of x, must not satisfy the confidence threshold as well. So, what the confidence based pruning theorem says, if x belongs to y minus x does not satisfy the confidence threshold, in that case x dash belongs to y minus x dash also does not satisfy the confidence threshold. To prove this theorem, consider the following two rules: x dash belongs to x minus y minus x dash and x belongs to y minus x, where x dash is a subset of x. The confidence rules are sigma of support of y by support of x dash and support of y by support of x respectively. Since x dash is a subset of x, then support of x dash is greater than or equal to support of x. Therefore, the former rule cannot have a higher confidence than the later rule. So, now rule generation in a priori algorithm. So, as you know, the a priori algorithm uses a level wise approach for generating association rule, where each level corresponds to a number of items that belong to the rule consequent. Initially, all high confidence rules that have only one item rule is consequent are extracted. Then these rules are then used to generate the new candidate items. For example, if ACD belongs to B and ABD belongs to C are high confidence rule, then the candidate rule AB belongs to BC is generated by merging consequence of both the rules. Okay, so we will see the lattice structure over here. Okay, so here let us take this lattice structure. Okay, so now here what we have taken is ABCD pruning of the association rule using the confidence measure. So, now here suppose the confidence of BCD of A is low. So, now this is a lattice structure that is generated ABCD whose confidence is greater than some x value which is not known. So, now BCDA of A confidence of BCDA is greater than or equal to A. Now, if this is a low confidence rule, then wherever A is involved, wherever confidence of any item set is greater than AC, all those are low confidence rules. So, now BCD will equal to greater than or equal to A is a low confidence rules if it is proved, then all the values or all the subsets which are having or all the item sets supersets which are having, if their value is greater than A, wherever A is involved, all those are low confidence rules. And all these when we find that these are the low confidence rules, then these can be proved. Pruned means these can be cut from the lattice structure because they does not generate any frequent item sets. So, only ABCD, ACD greater than B, ABD greater than C, ABC greater than D, BC, BD, CD and BCD, all these are high confidence rules and all these things are low confidence rules, where we are applying the confidence based pruning. Means based on the confidence we are eliminating these items from the lattice structure, which will generate less amount of frequent item sets. So, rule generation for a priori algorithm, what it is, for each frequent k item sets f of k greater than or equal to 2. So, now do, now here h of I I belongs to f of k, one item consequent of the rule, call app generation rule. You calculate all the generation rule, and if you find that any one of the item set is having low confidence rule, and all its subsets supersets which are being formed, all they are found to be low confidence rules, and that can be eliminated from the list according to the theorem. So now consider, for example, here they have taken one example where the list of binary attributes from the 1984 United States congressional voting records. So you can find out different the UCI machine learning repository is used here. So Republican, Democrat, handicapped infants, and then water project cost sharing, yes and no, budget resolution yes or no, physician fees yes or no, then aid to EI Salvador yes or no, religious group in schools yes or no, anti-satellite test ban yes or no, then aid to Nicaragua is yes or no, MX missile yes or no, immigration yes or no. So all these things are there. So based on the voting done during 1984 United States Congression. So now budget resolution no, mission missile is said no, then aid to ASL S, then it all belongs to a Republican, then confidence is 91%. So budget resolution S, missile X and Salvador no, it belongs to Democrat 97.5. So where the crime no, right to issue no, physician free no, free fees no, physician fee freeze no, Democrat belongs to a confidence of 100%. So now this is how an example where we calculated we used a machine learning algorithm to calculate the confidence, and based on that we can find out which are the low confidence values and high confidence values. Okay, next moving to the next concept, maximal frequent item sets. So what is an maximal frequent item sets? Okay, so according to maximal frequent item sets, what a maximal frequent item set generation says, maximal frequent item set is defined as an frequent item set for which none of its immediate supersets are frequent. What is the definition? Which set you called as a maximal frequent item set? An item set, a maximal frequent item set is defined as a frequent item set for which none of its immediate supersets are frequent. To illustrate this concept, consider the latest structure shown in the figure 6.16. So here, maximal frequent item set. So now, so this is null A, B, C, D, E. So now by combination we get A, B, A, C, A, D, A, E, B, C, B, D, B, E, C, D, C, E and D, E. Then combination of all these things A, B, C, A, B, D, then A, B, E, A, C, D. Okay, all these things. So now here we have drawn a border called as frequent item set border. Frequent item set border. So frequent item set border is being drawn. So which separates. So this border separates the item sets which are frequent and which are infrequent. So these item sets are frequent item sets, and these item sets are infrequent item sets. Okay, so now if we take, so consider if AB is a non-frequent item set, then wherever this is involved, where it is being formed ABC, ABD, ABE, ACD, ADE, ABCD, ABCE, ABDE, ACDE, ABCD, all these are infrequent item sets. Now what is maximal frequent item sets? So now AD is called as maximal frequent item sets. Why AD is called as frequent item sets? Now AD, it is going to ABD, it is non-frequent. ED is going to ACD, it is also non-frequent. So according to the maximal frequent item set rule, so an item set is said to be a frequent, maximal frequent, if its immediate subsets are infrequent. So AD's immediate immediate subsets ABD and ACD are infrequent. So AD is a maximal frequent item set. Then similarly ACE, so for ACE, ABCE and ACDE, these are also again they are infrequent item sets. So ACE is also comes into the category of maximal frequent item sets. Now you take for example this AC. Now AC, why AC is not frequent item set, maximal frequent item set? Because AC here, ABC is non-frequent item set, but AC is going to an item set of ACE which is a frequent. So now AC cannot be a maximal frequent item set. Similarly BCD, so its immediates. So after that ABCD, its superset ABCD is non-frequent. So once we classify the difference between once we find out frequent and non-frequent item sets, and once we draw a frequent item set border, so at the border we find some of the item sets which are maximal frequent. So maximal frequent item sets are those whose immediate supersets are infrequent. So now coming to the next concept, what is this is again the same explanation what I did. Now what is a closed frequent item set? Closed frequent item set provide a minimal representation of items without losing their support information. Okay, so what is a closed frequent item set? A closed frequent item set provide a minimal representation of item sets without losing their support information. So what is a closed item set? An item set X is closed if none of its immediate supersets have exactly the same support count as X. An item set X is closed. What is a closed item set? An item set X is said to be a closed item set if none of its immediate supersets have exactly the same support count as X. Put it another way, X is not closed if at least one of its immediate supersets has the same support count as X. So now how we will see? Let us see this with an example of an example with ladder structure. So now here, so now A is so these item sets which are with a gray circle, they are all called as closed frequent item sets. So how we define a closed frequent item set? So now you take first A. A has occurred in how many transactions? 1, 2 and 4. Now its immediate supersets AB is 1, 2. Now here transaction is 3 and here transactions are 2. So now this can be made it as closed superset, but the immediate transaction you see AC which has occurred in 3 transactions 1, 2 and 4. So for this reason A cannot be a closed item set. So now minimum support count how much it is here? 4. Now you take B, it has occurred in 3 transactions 1, 2 and 3. So wherever B is involved, here it has occurred in 2, here according to this it may be a closed, but here B it has occurred BC, it has occurred in 3 transactions, so B cannot be a closed item set. Now how C is closed item sets? Let us see, C has occurred in 4 transactions 1, 2, 3 and 4. So now wherever C is involved, AC, here it has occurred in only 3 transactions, here it has occurred only in 3 transactions, and then here it has occurred in 2 transactions, here it has occurred in 2 transactions and here also in 2. So here it has occurred in 4 transactions and all the remaining transactions are 3, 3, 2, 2 and 2. So C is closed frequent item set. Why this is closed frequent item set? Because here it has occurred in 4 transactions and here it is occurred in 3 or 2 transactions. So C is a closed frequent item set. So similarly, you take D has occurred in 3 transactions, but its immediate supersets now wherever it is. So here you take it has occurred in 2 transactions, then here is also 2, here it is also 2, so D is also a closed frequent item set. Then you take ACD. ACD is also a closed frequent item set because here it is occurred in 2, here it has occurred in 2, and here it is occurred in 1. So here it is occurred in 2 transactions, here it is occurred in only 1 transaction, and here also only 1 transaction. ACD is occurred in transaction number 2 and 4, whereas ABCD it is occurred in only 1 transaction, that is transaction number 2, and here it is occurred in only 1 transaction, that is transaction number 4. So for this reason, these reasons ACD is a closed frequent item set. So hope you understood what is a closed item set. A closed item set is one whose immediate supersets are having less support. Less support means here it is having occurred in 4 transactions. If its immediate supersets are occurring less than 4 transactions, then that can be taken as a closed frequent item set. Okay, next coming to the next part, alternative methods for generating frequent item sets. What are the different methods are available for generating frequent item sets? So one is a priori algorithm. A priori is one of the earliest algorithm to have successfully addressed the combinational explosion of frequent item set generation. So now, despite significant performance improvement, the a priori algorithm still incurs some considerable IO overhead, input output operation overhead, since it requires making several passes of the transaction data. So for these reasons, a lattice a priori algorithm is a bit expensive. Then coming to the next one, traversal of item set lattice. What? A search for frequent item sets can be conceptually viewed as a traversal on the item set lattice. So means traversal item sets, search for the frequent item sets either from the top of the lattice structure or from the bottom of the lattice structure. Okay, so this is how we have 3 methods. So one is general to specific method, second one is specific to general, and third one is bidirectional. So now this is, now if I draw the frequent item set border from the top of the lattice structure. So here we are having a frequent item sets from A1, A2 up to A of n. So if I draw a border of a frequent item set border, so initially null this 3 dots, and whereas the dark dots represent the non-frequent item sets, and these are the frequent item sets. So if I draw a frequent item set border from the top of the lattice structure, then that type of method, association analysis, is called as general to specific. Now the same example, if I draw the frequent item set border from the bottom of the lattice structure, where these 3 represents the frequent item sets, whereas the rest of the things represents non-frequent item sets. Now if I draw a frequent item set border from the bidirectional as well as from the top as well as from the border, so these dots which are clear and the dots which are the circles which are dark, they are infrequent item sets, and these all things from both the sides, from the up direction as well as from the bottom direction, we are considering the count and we are calculating the frequent item set. This is another method, so where we can use it. So next method is breadth first versus depth first. So a prior algorithm traverses the lattice in a breadth first manner as well as in depth first manner. How it is? So here, or one more method is equivalence class. So before going to the breadth first versus breadth versus depth analysis, we will go equivalence class. So what is? Okay, so here in equivalence class, what we do, the level wise strategy is used in a priori algorithm can be considered to be partitioning the lattice basis on the basis of the item set, that is algorithm discuss all the frequent item sets first before proceeding to larger item set. For example, equivalence classes can also be defined according to the prefix or suffix label. So here in equivalence classes, how we can calculate the frequent item sets based on the prefix or suffix labels of an item set. So here how this is done. So here you take an example of the two lattice structure. So where we have done the classification based on frequent item set equivalence class, the classes which belong to the same group, they are called as equivalence class. So how we separate the equivalence class based on the prefix and suffix. Prefix and suffix. So this is prefix tree and this is suffix tree. What we have done in a prefix tree. So prefix is the first letter and suffix is the last letter. So now if you take suffix prefix a, now whatever the item set we start with a. So a, ab, ac, ad, abc, abd, acd, abcd, all these things are one group, one prefix tree. Then all the item sets which come in b, bc, bd or bcd, they all start with b, they are into another group, and this starting with c, this is into another group, and d, there is no item set other than d, this group. So d is alone. This is prefix tree. Now suffix tree, in suffix tree what we are doing, the last letter. So now here a, so none of the items end with a. So now if you take b, this is b and this b end with both the item sets and with b. Now here c is the suffix, this ac, bc, abc, all they end with the c as a suffix. Here all these items end with d as a suffix. So this equivalence classes can be generated based on the prefix and suffix labels of the item sets. So next is how this is being done, breadth versus breadth. What is breadth and depth first? The applied algorithm traverses the lattice in a breadth first manner. So in breadth first manner what it does, it first discovers all the frequent 1 item sets followed by the frequent 2 item sets and so on until no new frequent item sets are generated. So in breadth first what we are doing, so here we are taking, so now level 1, its next level, so depth we are going, then these item sets until no further item sets are being drawn. So this is breadth wise. So here all these things, so all these things are frequent item sets. Traversal, this is what I am finding out, traversing along the breadth to find out the frequent item sets. So now here in a depth analysis what we are doing, we are going in depth, we are not traversing in horizontal way, we are traversing in vertical way to find out the most frequent item sets. So that is depth first method. Okay, so this FP growth algorithm is already being covered into the previous lecture. Okay, the next point is evaluation of association patterns. So the last topic in module 3, is evaluation of association patterns. There are different methods to go for this. So okay, so evaluation of association patterns. Associated rule algorithm. So here again I am using the notes by Sandeep Kumar from Cambridge Institute of Technology. In the previous document, this document is your textbook and this document is the notes from the Sandeep Kumar from Cambridge University. Okay, so now evaluation of association patterns. So now which association patterns are performing well or no, we need to evaluate that thing. So association rule algorithm tend to produce too many rules. Many of them are uninteresting or redundant. Okay, redundant. So how it is uninteresting or redundant? Redundant if ABCD belongs to D and ABD belongs to D have same support and confidence, then such type of rules are called as redundant. Then in interestingness, measures can be used to prune or rank the derived patterns. So there is one measure called as interestingness measure, which can be used to prune or rank the derived products. So, what are the objective measures of interestingness? So, given a rule, if you take a rule x belongs to y, information needed to compute the rule interestingness can be obtained from the contingency table. Contingency is a table for x belongs to y. So, here let us take contingency table. So, here on the vertical side we have x and on the horizontal side we have y. So, what is f of 1 1? F of 1 is support of x and support of y. F of 1 0 support of x and support of y. F of 0 1 is also a support of x and y. F of 0 0 is also support of x and support of y. Then what is f of 1 plus and f of 0 plus? What it is? So, let it is f of 1 plus will give you the total of x of y to x of y. So, that is the interestingness factor, and this is interesting factors. Okay, so now let us take this with an example. So, how we calculate this interest factor? So, interest factor I of a comma b, a is one item and b is another item. So, I of a b equal to support of a b divided by support of a into support of b. So, n into f of support of what is support of a b, both together if you take this is n into f of 1 1 by f of 1 plus f of plus 1. So, that is what its value will r. Now, how we have defined this a and b are based on the interest factor. So, if a and b it is equal to 1, if it's this interest factor is equal to 1, then it is proved that items at a and b are independent. So, if the value of this interest factor a and b is greater than 1, then a and b are positively correlated, and if its value is less than 1, a and b are negatively correlated. Okay, example you can take. Okay, so example here tea, coffee we have taken, tea 15 and coffee 5, total is 20, tea, coffee is 75 and here 5, total is 20, and this is 75 plus 15 90, this is 5 plus 5 10, this is 100, 20 80, this is also 100 and here is a total 100. Okay, so this is f of 1 plus and f of 0 plus 0, and this is n, total n. For the coffee tree example shown in the figure, so what is the interest factor I? I is equal to 0.15 divided by 0.2 by 0.8, support of AB. So, this is tea and coffee, I of A and B, this is 0.15 divided by 0.2 into 0.8, that is equal to 0.9375, thus suggesting a slight negative correlation because this value is less than 1. So, tea and coffee are having a negative correlation between the tea drinkers and coffee drinkers. So, tea drinkers and coffee drinkers, if you take both these, they are having negative correlations. So, next is IS measure. So, IS is an alternative measure that has been proposed for handling asymmetric binary variables. So, when the variables a and b are asymmetric binary variables, so here the measure is defined as follows: IFS a comma b is equal to root of I a b into support of s of a comma b. So, support of a comma b root of divided by root of support of a into support of b. So, now a correlation analysis. So, correlation analysis. So, for binary variable, correlation can be measured using the D coefficient, which is defined as D coefficient. So, D coefficient is equal to f of 1 1 into f of 0 0 minus f of 0 1 into f of 1 0 divided by root of f 1 plus f of plus 1 f of 0 plus f of 0 plus. So, the value of correlation released from minus 1. So, if the value of this correlation D coefficient is minus 1, then perfect negative correlation. If its value is plus 1, then it is perfect positive correlation. Okay, so these examples you can go through the notes. Everything is solved over in the notes. These all things I've already covered. How to calculate confidence and support. So that's at the end of these notes you have so many questions available. Question bank is available. You can refer these question banks for the final exams as well as for the internals. Okay, so the same thing it is being covered over here. You can cover, you can look out onto this. Okay, these are all solved examples available. You can solve these solved examples one by one. So if you have any doubts, you can contact me. So that's the end of module 3. Hope all of you are taking uh, corrective measures against COVID-19. So all of you, I request all of you to be stay in your home, don't go outside, as coronavirus is spreading very fast across the state and across our Belgaum district as well as our Bijapur district. Everywhere, Bagalkot district, it is spreading. So take care of yourself, stay home, stay safe, and have good luck. Thank you.